Swayam Prabha. Digital India. Educated India.
Last class we have seen about hydrograph, unit hydrograph, derivation of unit hydrograph, conversion of 1 t-hour unit hydrograph into different d hours unit hydrograph, where m is integer and as well as m is fraction, and also studied about synthetic unit hydrograph. All these things are just to know what is the quantity of water flowing in a stream for the given rainfall. In case if the rainfall is more and the water level in the river crosses its banks, then we call that quantity as floods. If that quantity is much well within the banks of the river, we call that as peak flow. But once the moment it crosses the river banks and inundates the area, leading to economic loss or life, we call that as floods. So we will study about that, how to estimate that much quantity of flood flow. We cannot measure it, only we can estimate it, right? So thus a flood is an unusually high stage. Please remember this stage. We have studied stage discharge relationship. Which stage is the level where we have not measured. So that is a high stage in a river, the level at which the river overflows its banks and inundates the adjoining area. Because flood causes loss and or damages in terms of economic loss, loss of life, loss of property. Also, it spoils the image of country's infrastructure facility. Oh, this country is flooding every semester or every monsoon, and this country floods even for a small rainfall. So it gives a bad image about infrastructure. Right? So somebody said that one picture gives a meaning of 1,000 words. So this is an example for a flood. It means the quantity of water which we cannot measure, and it also inundates the adjoining area. What happens when there is a flood? We call that as a disaster. It's one of the natural disaster, right? It inundates the property, restricting the movement of life, leading to huge economic loss, not only in urban area but also in rural area, right? These are all some of the example photographs. Every country faces one day or other day a devastating flood. Mumbai, New York, several countries. Every year some countries are facing drought as well as floods. These are all some of the flood damages. Normally the flood damages happening in a urban area is come to known to everyone because of mass and media. But there is another location where there is a flood damage, that is in command area or in the agricultural field. Nobody reports it, and we will come to know that loss only when next crop year we have an increased cost of our staple foods, right? So these are all the cause flood damages, and this is simple statistics given by Central Water Commission. At an average year where there is no special floods, the area affected is 7.351 million hectares per year, and population is 40.967 million. Human life is almost 1,790. Cattle's lost 85,000. More than 14 lakhs houses gets damaged, and the cost was 370 crores. The crop hectares is almost half of that area affected, 3.725 million hectares, right? The total area affected is at an average 7.3. Crop area is almost 50%, 3.7 million hectares. Crop damage, right, is almost 3 times the cost damaged in house. But we come to know more about these house damages than these crop damages. 1095 crores. Public utilities, right? Infrastructure, electricity, cables, right? Buses, all these things, roads, 1186 crores. So at an average every year around 2700 crores is the flood loss as reported by CWC. Why this damage is happening? Because whether we have properly estimated the expected peak flow and designed our infrastructure to that capacity. Because millions of rupees are spent on flood forecast, flood control and flood mitigation, especially in urban area, because more urban population. Rural area, it is agricultural lands. So thus, estimation of flood peak is the most important parameter considered in the design of infrastructure, especially related to water resource facilities. Right? What is this peak flow? Peak flow is nothing but it's the flood magnitude or discharge as well as time to peak in our hydrographs. Normally it also tagged with the frequency, that is return periods, like 1 in 100 years return period, 1 in 50 years return period. Whether my constructed infrastructure can take the flood of 1 in 50 years or 1 in 100 years. That depends upon the importance of the structure. There are several methods available to estimate the flood. Out of all, as usual in hydrological phenomena, the first method is empirical method, right? A dimensionally non-homogeneous equation. The second method is rational method. The third is unit hydrograph techniques, and fourth is flood frequency studies. Since there are several methods, I'm listing only four. There are several methods, but which method we have to select to estimate the flood in my area, so that I can construct a infrastructure like a culvert or a road bridge or a dam or a weir or a barrage. So the flood estimation method selection depends upon my desired objective. For what purpose I am estimating. Second one is the available data, whether a longer length of available discharge or observed discharge is available for longer length, whether the peak flows have happened continuously for several years, right? Then the other factors is like technical factors. There are certain methods which I can use for large area like hydrographs. I cannot use it for more than 5,000 kilometers square if the catchment is, right? So it is not just a single thumb rule which guides the selection of flood estimation method, several points as listed. Let us see one by one. Empirical method, everybody knows that it's a site specific regional based formulae based on the statistical correlation and other important catchment properties. Initially, long time back, one of the important catchment property is area of the catchment. So like our discharge estimation using empirical methods, in this case also the peak flood or the peak discharge is estimated as a function of area of the catchment. Since this is a dimensionally homogeneous, we call this as empirical methods, where QP is in meter cube per second and A is in kilometer square. Some of the famous formula which are used in India, first one is the Dickens formula 1865. Right? He said that peak discharge is equal to a coefficient called as Dickens coefficient into area of the catchment to the power of 3 by 4. And he has given various values for this CD depending upon the location. Right? And its value varies between 6 to 30. Right? Like North Indian plains, it is 6, hilly regions, it is 11 to 14, central India and coastal Andhra outside is 22 to 28. So the coefficient says where we can use this formula. Right? The second is very famous Rice formula, which is very much useful in southern region. It's developed in 1884. He says that QP is CR or CR is nothing but rise coefficient, again catchment area to the power of 2 by 3, right? And he has given this CR for different space or different location, estimating a distance from the coast. The CR is 6.8 if the area which you are estimating the flood is within 80 kilometers from the coast, or CR is 8.5 when the area where you are estimating the flood is 80 to 160 kilometers from the coast, or 10.2 if it is a hilly area, that means above 160, where you can see the Western Ghats, right, from east coast. This is mainly used in Tamil Nadu, Andhra Pradesh and Karnataka, eastern side. Sometimes it is also presently in useful. Right? Then English formula, remember English and deserves a formula to estimate discharge. Here also English gave a formula to estimate the peak discharge, which is function of catchment area A. So this was originally developed for the Western Ghats catchments in Maharashtra, and now it is used in all over Maharashtra with a modification in the numerator to shoot the site specific. It is non-linear. It is 124a divided by square root of a plus 10 power 4. If you want to change these numerical values, then again you have to do a regression equation for different units. Then this is for Indian basis. Now, not only in India, in several other countries also, initially it was the empirical methods they have developed. This is the first formula by Fuller's, which incorporated the frequency or the return period as a function of peak discharge. So then once he has introduced the peak discharge for a given return period, QTP is CFA to the power of 0.8, 1 plus, that means it's an empirical equation, and this CF is the Fuller's coefficient, values between 0.18 to 1.88. He has used it for different catchments, especially in US. Then this Baird and McIlwraith in 1951, they have slightly modified our English formula, which has A both numerator and denominator, by incorporating the flood data, recorded flood throughout the world, right? So with a small estimation error, this QP by Baird method can be used to estimate the flood throughout the world. So these are all some of the empirical methods, right? So then what happens after a certain period, these empirical methods become site specific. For intermittent area, it becomes very difficult to estimate. Then there are certain graphical method which was developed, same like our empirical method. Here also, instead of equations, the peak discharge values are given as a function of catchment area in a graphical form, right? For Indian rivers, Conversine and Popov was developed 1967. Right? It's a rough estimation. Right? You can see that the drainage area is nothing but the catchment area in x-axis in kilometer square, and discharge in y-axis in meter cube per second. Right? It has given for southern Indian rivers, northern and central Indian rivers. Please note the scale in both in x-axis and y-axis are in logarithmic scale. Okay, so in logarithmic scale only the relationships of linear, otherwise it is highly non-linear. So once I know the drainage basin area, then I can find out what is the peak discharge depending upon where my rivers are. So these types of curves are also in use for Indian rivers. But normally empirical methods sometimes very good in estimating, and it's slightly at a safer quantity, right? For large infrastructure, we can still check our estimated method with these empirical methods. When my objectives are very small, or my infrastructure is small, or like my stormwater drainage, where every 5 years once, 10 years once, I modify the size of the infrastructure, we need another method. Otherwise, unnecessarily, we will be constructing very large infrastructure. Right? So one of the such method is rational method, right? Let us assume that there is a rainfall continuously happening, right? So the top one is the hydrograph and bottom the runoff also goes on increasing. If the rainfall is still continuing even after the time of concentration, the discharge becomes constant, and that is the peak discharge. Okay, that means when my peak discharge is area of the catchment into intensity of rainfall, directly proportional. And to remove that directly proportional, it is multiplied with a coefficient called as runoff coefficient. So in rational method, QP is equal to runoff coefficient, the area of the catchment, and intensity of rainfall. How to select this intensity of rainfall? In this case, the intensity of rainfall, the duration of rainfall should be more than time of concentration. Once my duration of rainfall is more than the time of concentration, go to our IDF curve. For that time of concentration estimation, find out what is the intensity of rainfall, and then substitute that in this case, right? Then use appropriate intensity of rainfall, appropriate unit. Intensity of rainfall will be in per hour, and area will be sometimes hectares or kilometer square. Use same unit so that area is also in meter square, I is meter per second, then only your QP will be meter cube per second. And then this runoff coefficient is a function of land use. Right? So we will see these two parameters very in depth. Time of concentration is the time taken for a drop of water from the farthest part of the catchment to reach the outlet. Empirical equations are available to estimate it. Right? You can remember this. We have used this in synthetic unit hydrograph or Sinder's method. Time of concentration or time to peak is a regional constant L into LCA by square root of S to the power of n, right? Where L and LCA are length of the basin and length of the water course. S is the slope of the basin. Either you can use this method or we can use Kirpich equation developed in 1940s, where my time of concentration is function of length of travel, which is equal to LCA, and slope. It's an empirical relationship. When we know these two values of the catchment, I can estimate the time of concentration. Once I know the time of concentration, bring back your IDF curve, intensity, duration, frequency curve of that area. For the duration equal to Tc, estimate what will be the intensity of rainfall for different return periods. Right? For the same duration, you will have different curves. So if you want for 25 years, go to the 25 years return period curve and pick up the intensity of rainfall. That is selection of I. Second one is selection of runoff coefficient C. It represents the integrated effect of catchment loss. That means if the loss is more, then runoff will be less. If loss is less, runoff will be more. So it is nothing but the nature of the surface. Sample values of the runoff coefficient used all over the world. It is function of our land use and values. For example, urban area, right? Or its values varies from lawn or varies. We are more on streets in urban area, 0.7 to 0.95. In agricultural, this is 0.5 to 0.3. Okay, so this is about C value. So once I know the C value, intensity of rainfall, time of concentration, and area of the catchment, we can simply estimate what is the peak discharge. I have given an example. So an urban catchment has an area of 0.85 kilometers square. Okay, the slope is 0.006. The maximum length of travel of water is 950 meters. So the maximum depth of rainfall for 25 years return period. That means I have given the IDF curve in terms of table. So for 5 minutes duration, 10 minutes, 20, what is the depth of rainfall, right? If a culvert of the drainage has to be designed for a return period of 25 years, because I have a return period curve for 25 years, so I am giving a question of 25 years. Estimate the required peak flow rate. Assume the runoff coefficient as 0.3. Okay, so the first step is estimate what is the time of concentration. Since L and S are given, estimate what is the value. So substituting this L is in meters, S is a slope. So it's an empirical relationship. So I am getting a value of 27.4 minutes. So go to our IDF curve. For duration of 20, I have 30, I have interpolate for 27.4 minutes. What could be the depth of rainfall? So by linear interpolation between 20, for 20 minutes it is 40 millimeter, for 30 minutes it is 50 millimeters. For 27.4 minutes by linear interpolation, my maximum depth of rainfall is 47.4 mm. Now I need rainfall intensity. Intensity is depth per time of concentration. What is the depth? 47.4 mm. Time of concentration is 27.4 mm, which is equal to 1.73 mm per minute or 103.8 mm per hour. Now I know the rainfall intensity, multiply it with the runoff coefficient 0.3 into 103.8. This is mm per hour. I am converting this into meter per second. Then 0.85 kilometer square, convert that also into meter square into 10 power 6. So my maximum runoff for this small area is 7.35 meter cube per second for a return period of 25 years. Okay, this is how we estimate the hydrologic discharge for a given return period. Then if you want to design the channel, take this as the design discharge for your channel. Estimate what should be the expected width, depth and slope so that it is safely disposed. That is empirical method. Unit hydrograph method, I think we have seen much about this unit hydrograph. If I know what is the rainfall excess, then I can find out what is the peak discharge. If that rainfall excess is multiplied with the probable maximum precipitation, right? If my unit hydrograph values are multiplied with the probable maximum precipitation, that is the highest runoff, and I call that as the flood hydrograph. But if my rainfall is known for a given return period, then we can assume that discharge as that type of return periods. But when I measured this discharge, if I have measured for let us say 30 years, then I can estimate the flood magnitude using empirical methods only for a return period of 30 years. Suppose if I want to design an hydraulic structure for a flood discharge of 100 years return period, then my empirical methods may not be useful. Then I have to measure the discharge for 100 years. Then what happens in such places is flood frequency analysis, flood frequency studies are very useful. Especially it is like extrapolation of our rainfall, right? Using Weibul's method, Czechoslovakia method, all these things. But here we are fitting the observed flood values to a probability function. Okay. So the magnitude of the peak flood discharge is a necessary input for design of hydraulic structures. So the annual data of maximum flood. How to find out this maximum flood? Now every year, if I have estimated daily discharge in a particular year of 365 days, only one value is the maximum value. Like that you pick up the maximum value in each year of the observed discharge. Suppose if I have 50 years of observed discharge, then every year I pick up the maximum value. Then I will have 50 values, right? Year and flood discharge, year and flood discharge. That is called as annual data of maximum flood. Now you estimate the probability of exceedance using Weibul's method. That means same method, put it in a descending order, give the rank, then rank divided by n plus 1 will give you the probability of exceedance, and inverse of that will give you the return periods. Okay. So that's the flood frequency using empirical methods. Sometimes we can fit for a distribution. A good example is binomial distribution, which we have fit for our rainfall. Then main objective of hydrologic frequency analysis is, after fitting a particular distribution, you have to estimate the flood magnitude. Xt is the flood magnitude for a return period of t. X bar is the mean of the flood discharge, not the daily discharge, the flood discharge, daily annual maximum value. And sigma z is nothing but standard deviation of that maximum flood, and k is called frequency factor, which depends upon the return periods. This is the basic linear equation employed to estimate the flood frequency in all flood magnitude in all the flood frequency analysis, right? So there are several distributions available, but commonly used frequency distributions are Gumbel's extreme value distribution, log Pearson type 3 distribution, and log normal distribution. Let us see one. It's Gumbel's extreme value method, 1941. See, Gumbel's method is very widely used and very good. This method is most widely used probability distribution function for extreme value. It depends upon the extreme value distribution. What is Gumbel said is, Gumbel defined flood as the largest of every 365 days. That means he picks up one value in a year, and that series is called as flood series. So estimate the value of average and standard deviation, since it is using only two moments of the statistics, average and a standard deviation, right? Xt is x bar plus k sigma z. So this above equation, this frequency factor k gives you the solution of Gumbel's distribution. This is the Gumbel's extreme value distribution. It shows that n largest values of subsamples, right, follow the extreme value. Type 1 distribution is, you have average and standard deviation. So he says that the probability density function is alpha e. Suppose if I put alpha into x minus beta as y, then my probability density function is alpha into e power minus y minus e power minus y, where y varies between minus infinity to plus infinity. Similarly, the cumulative distribution function f of x is e to the power of minus e minus to the power of minus y. Now we need to find out the solution for this equation, where alpha is nothing but function of variance, beta is function of mode, that means x minus beta, right? And substituting the values of this value, we will get the value for y, that's the solution, right? For x minus x bar is nothing but the deviation from the observed values of the average, then standard deviation, right? So Gumbel's cumulative distribution function is e to the power of minus e. The solution here for y is minus ln of f of y, where f of y is nothing but again my Gumbel's cumulative distribution function. Suppose in practice the probability of exceedance p is the cumulative exceedance of the probability, then my solution for a given probability or given return period is minus ln of 1 minus p. But what is p in terms of return period? P t is equal to 1 minus p. Substitute this here, then my solution yt is minus ln of t by t minus 1. So since t is equal to 1 by p, the value of y associated with return period t is yt is equal to minus ln t by t minus 1. But this may not be sufficient to estimate for us. We need it in terms of numbers, right? For example, Gumbel's extreme value distribution looks like this. That means the mean median mode, right? It's slightly skewed towards the left. And Gumbel's equation says that in general yt, and on rearranging xt for a given return period is x bar plus k. So all other yt, sigma, xt comes with the coefficients, right? And on the other hand, it can also be written as This is for population. For large sample size, Kt is Yt minus 0.577. Suppose if the sample is very small, right, then the same linear equation to estimate the return period xt is equal to x bar plus k, but this k is estimated as a function of yt, which is the solution for our Gumbal's distribution minus ln of t by t minus 1, and this y bar n and s bar n is called as reduced mean and reduced standard deviation, which are functions of sample size n and the return period. For example, like this. Reduced mean in Gumbal's extreme value, I have n. This is sample size. This is for 10 years is 0.4952. For 11 years, 10 plus 1. 10 in the first column. 1 you add 1, 2, 3, 9, right? That will give you the 11th year, 12th year, 13, 14, 15, 16. So that means minimum data point required is 10. Then only I can estimate this. Similarly for standard deviation, reduced standard deviation. For 10 years it is 0.9496. For 11 years 0.9676. So thus once we estimate the value of yt based on the return period, substitute this to estimate the frequency factor, substitute it in the variate value xt after estimating the average and standard deviation of the flood series. So this is how Gumbal's value was used. For example, I have given a sample. The mean and standard deviation of flood time series of 27 years. That means I have 27 years of daily observed data, and every year I pick up one value. So totally there are 27 flood values. The average of that is 4,263 meter cube per second, and standard deviation is 1,433 meter cube per second. Now we have to estimate the magnitude of the flood for a return period of 10 years, 50, 100. That means t is equal to 10, t is equal to 50, t is equal to 100, and t is equal to 200. Now from the Gumbal's extreme value table for 27 years, find out what is the value of reduced mean and reduced standard deviation. For 27 years, this is 20, 21, 22, 23, 24, 25, 20, 27 years. It is 0.5332 is the reduced mean, and 21.1004 is the reduced standard deviation. So use these two values, and yt is minus ln of t by t minus 1. Now I have estimated for 10 years, yt is equal to ln is log base e into 10. T minus 1 is 9. So this is 2.25037. Then kt is equal to yt minus y bar n by s bar n 1.56. Substitute this k value in my linear equation. 4263 is the average value. 1.56 times of 1. So the flood for a return period of 10 years is 6,499 meter cube per second. Now you can estimate for 50 years, 100 years, and 200 years. For all these years also, my y reduced mean and reduced standard deviation remains same, because it is a function of only data points. But still the solution yt varies, right? Then you please estimate this xt, and you see, my question is, suppose if for 10 years it is 6,499 meter cube per second, for 50 years return period, whether the xt will be more than this or less than this. Yes, because as the return period increases, the magnitude also increases. So 100 years flood will be more than 50 and 10 years. 200 years return period flood will be more than 100, 50 and 10 years. Okay, so this is how we estimate the magnitude of the flood for different return periods. Okay, the other advantage of this Gumbal's extreme value distribution is, if I have 2 points in the distribution, I can estimate flood magnitude for any other return period. Now I have estimated the magnitude of the flood for different return periods. But how confident I am that my estimated value is exactly this value, right? If I want more and more confidence, then my range of value should be more and more. So the value of variate determined by Gumbel's method can have errors due to limited sample data. So the confidence interval indicates the limits about the calculated value which the true value can be said to lie within the error, right? For example, you see this figure, the solid line is the estimated magnitude of the flood. Please, in this x-axis is in written period, that is in log scale, and y-axis is magnitude of the flood, that is in natural scale. Now I have fitted this value. What is the confidence that my estimated value lies on these points? I only estimated, but in real life, whether it will be exactly lie here or within a range. Then if my confidence is larger and larger, then I give a more range. That means my estimated value is this, but actual value may be between this point to this point, right? So that is why confident probability C, the confidence interval on the variate xt is bounded by values x1 and x2. Here x1 by 2 is nothing but x1 and x2, which is equal to xt is the estimated value using Gumbel's method for different return periods t, plus or minus a function of confidence probability C, and then a probable error SE. Then Gumbel has given this relationship. If C is in percent, that is confidence probability 50% to 99%. That means I am 99% confidence, 50% confidence. Then my f of C is this value. As my confidence limit is increased, then my range is larger. That means I have constructed a large facility, so it can accommodate any flood. So my confidence limit will be larger. This probable error is estimated as a function of that frequency factor k for a given return period, because these values vary for different return periods. The probable error. So sigma n minus 1 is standard deviation, n is number of data points which we have used to estimate. So after substituting for each k value, each and every estimated flood magnitude for a given return period will have one upper value and one lower value for a particular confidence limit. If I plot that, then my graph comes like this. You can see here the 95% confidence limit, the values are much more than the 80% confidence limit, right? If it is 99, the range will be much more higher. Okay, so that is confidence limit estimation in the estimation of flood magnitude for a given return period t. Mostly we say that this is the designed discharge, but actually we will be designing with the confidence limit. But while operating the reservoir for flood studies, we will work with the lower limit. Once my flood level reaches the lower limit of the confidence limit, then we start operating the dam. Okay, that is for safety, and this is for construction purpose. Right? So that is about log Pearson type. Sorry, that is about Gumbel's extreme value distribution. That is type 1. If you see carefully the equation which we have used, it used average and standard deviation, only two moments of the sample statistical properties, right? Average and standard deviation. Suppose if the probability doesn't follow normal distribution or extreme value distributions, that means third and fourth moment is also required. How will you convert? How will you use your data which is not following normal distribution to follow a normal distribution? First one is transformation. You transform the observed data into a different transfer, like taking log of all the data and then try to fit it in a normal distribution. It may follow. That is transformation. Like that, log Pearson type 3 distribution gave or used the third moment of the statistics to estimate the flood discharge. But for this, what he did, first each and every observed flood data is transformed into a logarithmic series. That means take value of if x1 to x27 or x30 is the observed peak flow in each year, take log of each value. Then take the average and standard deviation of that log series. Then for that log series, estimate what is the coefficient of skewness. That is the third moment. It may be positive or it may be negative. Once we know the value of CS, then for any return period, whatever the return period, that's why they say that the frequency factor is function of return period and coefficient of skewness. Log Pearson has given a table which shows the skewness coefficient varies between +3 to -3 for normal distribution. And then the return period varies from 2 years to 1000 years. If you want in between, we have to interpolate linearly between the skewness and the return period. So log Pearson type 3 uses the skewness values, that is the third moment, to estimate the flood. Then after estimating kz, you will get a value of zt. Take anti-log of that zt, that will give you the flood magnitude by log Pearson type 3 distribution. Okay. So I have given a sample. Estimate the flood with 50, 100, 200, 500 and 1000 years return periods using both Gumbal's value, extreme value distribution as well as log Pearson type 3 distribution. And then compare the values, and also for confidence limit of 80 to 99% to Gumbal's method. So now I have this frequency studies. I am able to estimate the magnitude of the flood for different return periods. But I have certain limitations of these frequency studies. The first limitation is the length of the data which I have used. For example, even if I have 100 years of observed discharge, I have only 100 data points. Right? I have daily discharge of 100 years, then my flood series will have only 100 points. So whether that data length is sufficient to represent the flood scenario of that river basin, still a questionable. But researchers say that a minimum number of data points required is at least for 30 years. That means minimum 30 data points are required. That is also the principle of statistics and probability, right? The minimum sample size should be 30. But in extreme value Gumbal's distribution, we can even adopt if the data length is for 10 years, because the value starts with the 10 years data points. Secondly, it is assuming that there is no changes, right, in the observed data point. That means there is no climate change, all these things. Then only we can use this frequency analysis. Right? Before going to that, one small topic. Earlier, people used to take the observed discharge at a station and do the frequency analysis. Several methods. They have fitted several distributions, but that is the flood at that particular site. But now what happens, over the period of the time, they found that there is a connection between the region and the flood. Then people started using this analysis called as regional flood frequency analysis. For example, if it is flooding at one basin, it will be definitely going to flood in the adjacent basins. How much is that region uniform, or how much is the homogeneous region? All the homogeneous regions will have same magnitude of the flood quantile. The equations for estimation of the flood may be different, but the return period of the floods remains same. Okay, so now the study of flood frequencies have moved from at-site flood frequency analysis to regional flood frequency analysis. Several methods, out of which L moment method is the widely used method for this regional flood frequency analysis. People are using even fuzzy cluster means, artificial intelligence techniques. That's a recent research in this flood frequency studies. I have estimated different return periods or magnitude of the flood for different return periods. Which one I have to consider to design my infrastructure? That is called as design flood. As I said, the design flood to be considered depends upon the objective. Like in the design of hydraulic structure, it is not practical to provide safety against maximum possible flood. So then, because economic consideration also should be taken care of. For small structures like culvert and stormwater drainage, it can be designed for less severe floods. For example, if I am uh, designing a stormwater drainage for a road with road bitumen, right, tar, then every 5 years once or every 2 years once, we may be relaying that road. When I am relaying the road, definitely my stormwater drain adjacent to that is going to disturb. That is why in olden days, the stormwater drainage, roadside stormwater drainage are designed for a return period of 2 years. But nowadays what happened? I am constructing the road with concrete. That means the life of the road is for minimum 30 to 50 years. Then that means I am not going to disturb that infrastructure for next 50 years. Then my stormwater drainage should also be designed for a return period of 50 years, depending upon the life of the road. Right? That is why now with increased material usages, my stormwater drains should also be considered for return period same as that of life of the adjacent infrastructure. If it is a natural drain I am supposed to design in an urban area, we have to consider it for maximum possible flood, that is flood estimated from PMP. Okay. Now we will see some 2-3 things. For example, design flood. That means it is the flood adopted in the design depending upon my objectives. Spillway design floods are, for example, it's the design flood used in the design of spillway, which may have a return period of very high. Spillway or culvert design flood, which may have a return period less than the spillway design flood. But from where you pick up this design flood? I pick up this design flood from standard project flood. What is the standard project flood? Standard project flood is the result of severe combination of meteorological and hydrological factors in that basin. Okay. For example, if the basin is larger and larger, then it may be flooding on the upstream side and also raining in the downstream side. Definitely the upstream side flood is going to come and join with the floods which is happening at the lower side. So then my project flood at lower side will be more than the project flood in the upstream side. Right? Standard project flood is also based on the catchment area and location. But from where you will get the standard project flood? It is estimated from PMF. PMF is nothing but probable maximum flood. How do you estimate probable maximum flood? You estimate PMP, probable maximum precipitation, use it in your hydrograph, estimate the peak discharge. 40 to 60% of my peak discharge estimated from PMP is called as standard project floods. Okay, why we have to worry more about this is the economics, loss of life. Once, if it is flooding due to surplus release from the dam is under control. If it is flow of water due to breach of a surplus weir is devastating. So my surplus weir should be sufficiently designed to take care of maximum flood. Right? This is certain guidelines suggested by Central Water Commission in India. It depends upon the type of structure recommended design. If it is spillway of major and medium dams, right, then we have to consider a PMF determined by the unit hydrograph or frequency with 1,000 years. If it is minor dams, weirs and barrages, standard project flood determined by unit hydrograph or flood with a 100 years return period. If it is a pickup years, 100 years to 50 years. Aqueducts, 50 years. Culverts, 25 years. Roadside stormwater drainage, nowadays that also for 25 to 50 years. Okay, so this is certain guidelines. Why we are more worried? Because unlike my normal discharge, where flow is within the bund, there is a risk in estimating this flood. What is the risk? It's the probability of occurrence of an event at least once over the period of n successive years I have considered, right? So R bar is nothing but the risk 1 minus probability of non-occurrence. What is probability of non-occurrence? It is 1 minus p to the power of n. So my risk is nothing but 1 minus p to the power of n, where p is 1 by t. Then what is reliability? How good I can rely upon this estimated value? It is the remaining of the risk, 1 minus r. That is nothing but 1 minus p to the power of n. But please note, the risk and reliability are governed by the economics and policy. I can design, I can take a risk. Okay, let every alternative year stormwater drainage floods. Then you design it for 2 years return period. Okay, it should not flood for once in 25 years. Then you have to consider the return period of 25 years. Then your risk will be small. But when we consider 100 years, it will never flood. Or it may flood only once in a 100 years. That is what risk and reliability are. Right? Over and above this risk and reliability, we also use safety factor, like factor of safety in your structural design. Right? You multiply with estimated stress strains with 2 times, 3 times, right? That is called factor of safety. Safe. Here, factor of safety in hydrology is actual value of the parameter adopted in the design divided by value of parameter obtained from hydrological consideration. Suppose if I, for a 100 years return period, I got a flood discharge of, let us say, 100 meter cube per second. I can design it for 150 or 200. Then my factor of safety is 1.5 to 2. But it should not be less than the hydrological consideration. So factor of safety will be always more than 1. Okay. So the difference between actual and adopted is called safety margin. So I just gave a simple problem. A bridge has an expected life of 25 years. Structural life. That means my return period, life of my structure is 25 years and is designed for a flood magnitude of return period 100 years. So my return period T is 100 years. Then what is the risk? Risk is 1 minus P to the power of N. What is probability here? 1 by 100. So the inbuilt risk of this design is 22%. If I have to reduce the risk for 10%, what return period rainfall I have to consider? It's a reverse. So if risk is 0.1, then 1 minus P to the power of 25 years, right? So my return period is almost 240 years. That is why as the risk, you go on reducing the risk, my return periods will be larger and larger. So magnitude of the flood will also be larger and larger. Okay. So dear friends, I am going to wind up with this floods. So you have to do certain self studies. For example, I said there are 3 most widely used frequency studies: Gumbels, log Pearson, and log normal. So I have not discussed about log normal. You also can study by yourself, the research study. Then what the flood series we have used is one data in a year. But if you carefully look the magnitude, the flood in 1 year may be half of the flood in the next year or in some other area, right? So in the same year which has maximum flood, this flood of year 1 may be a normal flow. So then what happens? You consider a particular, you draw a line, okay, magnitude of the discharge more than this or flood. Then you take the values above all that line in a year. So in particular year it may be more than 2, more than 10. So such series are called as partial duration series curves, and analysis can be carried out. Then as I explained, now the recent research is regional flood frequency analysis. Especially nowadays, if you see, there is a wide increase in the flooding area in India, right? Then if you want to see that, you can understand the cause and effect of flood in our area. Start from your hostel, then our IIT Bombay area, IIT campus, then Mumbai, Maharashtra, and then India. Go from small part to whole. So try to solve all the problems given in the class. Right? The current research in this area are to find out the suitable method for flood estimation, flood forecast, and flood warning. Okay. Then integrated flood mitigation program. Right? When you go for administrative services as a collector or a commissioner, then flood mitigation cannot be carried out in a single go. You have to do an integrated operation for the flood mitigation program. Now this integration word is used everywhere. Integrated water resources management, integrated drought mitigation program, integrated flood mitigation program. That means you take the help from different fields to solve a problem. And measures to reduce the urban flooding, to do a proper design of stormwater drainage system, the drainage of roadside drainage network, okay, estimation of flood magnitude for minimum risk, and flood frequency factors using artificial intelligence techniques, modification of rational formula, especially estimation of runoff coefficient. The other way is conserve the flood water. When rain is falling more and more, you store it more and more in the area, so your flood discharge reduces. These are all current research going on in this area of floods. Right? I have last question from these mathematical distributions. Right? Prove that mean annual flood used in hydrology will have a return period of 2.33 years. Okay. So friends, we are winding up our floods at this